Hello everyone, I'm KaiZhang from Royal Institute of Technology. Today I'm going to use about 10 minutes to introduce you our research work at KTH. First, I will share with you several slides about our research. So there we go. Uh, I'm a postdoc researcher and I'm working with Professor Christoph Duwig at the Department of Chemical Engineering. The topic we are working on is the wet combustion for clean and efficient energy. So what do we mean by wet combustion? It means we use the fuel. For example, we use methane or we use biogas or biosyn gas together with some kind of a steam dilution in order to reduce the emission, for example, the CO and NOx. And whether that wet combustion is going to help us reduce emission, that's a question, and we want to answer this. And a little bit background of our research here. So in the last several years, we have certainly seen an increase of temperature, and in summer, especially in Europe, we feel that it's getting hotter and hotter. According to the Paris Agreement on keeping the increase of global average temperature below 2 degrees Celsius above the pre-industry levels, different countries they have to do their own best to reduce the greenhouse gas emission in order to control the temperature. Without any policies used, we will very soon in 2010 see a temperature increase by about 4 degrees Celsius, as you can see on the left side. That's on the x-axis, you will see the probability of having different temperatures with different measures, with a policy or without a policy. So in the EU, they have decided to cut down 55% net greenhouse gas emission by 2030 compared to the 1990 levels. And in China, they decided to peak the greenhouse gas emission before 2030 and reach its carbon neutrality before 2060. However, there is the obvious fact that our country has developed and our technology has developed. There will be an increase of power requirement both in electricity and heat. So how can we compromise this? How can we develop our country? How can we benefit our society without causing that large amount of greenhouse gas emission? And how do we compromise for the increase of power requirements? We need technical solutions. We could use renewable energy, we could use some sustainable and decarbonized power. For example, we could use wind power, solar power, geothermal power. But all these kind of power are not that stable. And sometimes when we need it, it's not there. Sometimes when we need the wind energy, it's not there. What should we do? Of course, there is technology to solve it, but in a very long time run, we will have to depend on burning something. That means we will still need clean combustion technology. And how do we use the combustion to benefit the reduction of the greenhouse gas emission? Probably we want to make sure that the efficiency in our power cycle is higher. We want to increase our specific power output. Maybe we want to reduce the energy loss in our grid line. So we want some decentralized power generation. But anyway, we will have to develop some clean combustion technologies anyway. So what we mean by clean combustion technology, we mean that has to be of low NOx, emit low NOx, and we have to emit low CO, and we need some kind of technology to capture the carbon dioxide, of course. And of course, fuel turns to money by burning it, and that's you see that dollar sign there. And we want to upgrade our simple cycle to some advanced power cycles at a very low investment cost. We want high efficiency, of course. So those are some background of our research. So what we are actually using here, we are using high fidelity logic simulation to get the wet combustion. So why wet combustion? Because there are many reports about the benefits of the wet combustion. It reduced the NOx emission, it reduces CO emission, it gives you a high electric efficiency in some kind of cycle called humidified gas turbine cycle, and you inject the steam into the combustor into the combustor, and will basically change your behavior of flame, and that is going to benefit the whole cycle actually. So the motivation of our research here to use the high fidelity logic simulation is to promote our understanding of the wet combustion. And we want to develop some kind of efficient combustion system for not only burning the diluted methane, but also probably to burn some diluted renewable fuel using steam. That could be biomass, it could be biosyn gas or biogas. So many fuels, many cleaner fuels can be burned together with the steam in a wet combustion environment, and it will give us a very clean energy. That's our motivation. And of course, when we are trying to use this high steam in the combustion system, we are facing many challenges. For example, whether the combustion is going to be stable in the current burner, and whether that is going to give us some kind of a blow-off limit. What will be the flammability limit, and how does that depend on our running situations? And there are many things we have to consider. So we use high-fidelity logic simulation to guide the design of the combustion system, to guide the design of the combustor. So at the initial stage, where we stay at right now, we have designed the several conditions in order to run the simulation. We have set the thermal power in the combustor you have seen on the right side to 63 kilowatts. We set in the temperature of the steam diluted fuel at about 743 Kelvin. And why we have this high in the temperature is basically to help us to burn the steam diluted fuel in a very safe way. We want to make sure that this fuel is going to burn. It's not going to blow off when we are running it. This in the high enough temperature, of course, is not going to benefit the efficiency of the entire cycle. But what if this high temperature is from the recirculated gas, is from the exhaust gas? That is going to increase efficiency, of course, because we are extracting the waste heat, which will anyway be released to the atmosphere. Why don't we use it? And that will be very similar to compound cycle, but actually we have only a Brayton cycle inside. And except for that two conditions, we have set this parameter, as you can see, the omega there, that's the steam to air ratio in the mass flow rate. And we fixed adiabatic flame temperature to 1690 Kelvin, and by guarantee that by changing the steam to air ratio and equivalent ratio together, the two parameters together, we could fix that temperature. So a bit details about the conditions. You will see we have simulated several conditions, and I present you three conditions here. The natural gas, we start with natural gas, and that is the high temperature burning condition, 743 Kelvin. And the first case is a dry case, and the other two are actually wet case, 20% and 30% of the steam. And because we are actually using steam to replace the air within the cycle, it will basically reduce the power waste on driving the compressor. With the steam replacing the air, the oxygen content within the mixture will certainly decrease, say from the 20.1% to 13.6%. And with that high steam content, with that low oxygen content, can we still burn it? That's a question. And we have to simulate it. Maybe we could do experiment, but that's going to cost us more. We could start with the simulation and see what is the limit of the mixture. What would be the limit of having this steam content within our fuel, and it's still burnable. Now, if we decrease the oxygen content and if we increase the steam content, we will basically see an increase of the flame thickness. That is going to present us some kind of flame that is different from what you really see. And that is going to give us a lower and lower flame speed. And minimum here, we have a flame speed of about 13 cm per second. And on the left side, you can see we have three kind of flames simulated. And on the left side, the very left side, NGH0, that's a dry flame. That's something you always see in the conventional dry cycle. And that flame is kind of a V shape. And then when you increase the steam content, when you decrease oxygen content, you will see a flame that is more distributed, and you will probably see that it will give you a low NOx emission. And actually, we have even from the experiment, we have seen that NOx emission is below 10 ppm. You can see that these flames are actually getting larger and larger, and it's getting distributed. And basically, the flame is more homogeneous. It has a very homogeneous heat release rate, like this, and it's lifting up at some point higher and higher above the exit of the burner. So this is something interesting, and we would like to know about some details about what's happening inside. So we use chemical explosive mode analysis and what we call the explosive mode analysis to understand flame structure in the presence of in the presence of steam. We have seen that from the left to the right side, when we have different kind of steam content, we have classified the flame into different regimes. And a bit more details, you will be able to see that in our paper that is going to be published in field. So a bit of our outcome, we have done a quantitative analysis of different regimes associated with 4 flames. Actually, there is another flame which I haven't shown you here. And the wet combustion with 20% steam can perfectly replace the role of oxygen in assisting dry combustion. And wax combustion with 30% steam leads to more fluid particles defined in what we call a swirl stabilized region, presenting high tendency of local extinction. And with the high tendency of local extinction, that is going to also change the flame stability. And how does that going to change the flame flow interaction? That is also something we are interested in. As you can see here, that's also part of our outcomes. We have done a so-called proper orthogonal decomposition analysis to discriminate between large-scale and small-scale turbulence. And you can see here that's the decomposed fields of one of the flames. Some details you will probably see in our future paper, which we are going to submit. We have basically detected the existence of 2 sets of coherent structure, one with a structural number of 0.7, the one you see in this animation, the blue one, and that is very stable, it's always there, and the red one is not always there. What could be the reason behind that? What has driven to that? That's something we are going to report in our paper. So basically, we found out that the lifted flame is more stable, and there will be little interaction between the flame and the flow field. That's our research. Now, thank you for your attention, and that's all about our research. Certainly, we want something on the right. We don't want something on the left. We want a clean city, and that's what drives us to investigate more about this kind of new technology on the wet combustion. If you want to know more about my research, you can scan the barcode on the left side. You can contact me at your convenience. Thank you very much.